Hello class and welcome back. We are in week 4 and this week we'll get an introduction to amplifiers, both the BJT and the MOS version. So this is from chapters that we have already studied, chapters 5 and 6, 5 for MOS and 6 for BJT. But in those chapters I had skipped the second part of the chapters, the later half, but we had covered the first parts. So in this recording and this class and the next class, 2 recordings plus 2 problem sessions, I will try and finish the material in chapters 5 and 6 from this textbook, the 6th edition. Now, in the newer edition, the 7th edition of the same textbook, a lot of this material has been removed from chapters 5 and 6 and put in chapter 7 as a new chapter called Amplifiers. So I will also borrow a lot of material from the new new edition. Material is pretty much the same, but somehow it's a little better organized in edition 7. So some of my problems, you'll notice, have a number of from chapter 7, which means the new edition. Anyway, not to confuse you, I think as we start and move ahead, you should be able to see what I'm talking about. Okay, so let me expand this. So I will cover sections 6, 7, 8 from chapter 6 and 6, 7, 8 from chapter 5. This is MOS stuff and this is BJT stuff. Okay, and you'll find that a lot of the material is similar in how it's covered in the textbook. The same section numbers, the same approach. The only thing is the device will be either a BJT or a MOS, and the behavior of the circuit is slightly different because of the difference in the characteristics or the properties of the BJT versus MOS transistors, right? All right, so let me start with chapter 6 because as you know, I always try to do BJTs first and then MOS later. So following that trend, we'll do chapter 6 first. All right, so chapter 6, we are covering 6.6, 6.7, 6.8, and that finishes the chapter and the material on amplifiers. So in 6.6, in the textbook, we are introduced to basic BJT amplifier configurations. And you may or may not already have seen this before, but for the BJT, there are 3 configurations: the common emitter, the common base, and the common collector, right? There are 3 terminals in a BJT: the emitter, base, and collector. So if you make each of these common, and what does that common mean? We'll talk about it a little bit later. But it gives rise to 3 ways of connecting a circuit, right? And that's what this section 6.6 is all about. Well, before I go there, I wanted to bring in a table from the appendix. This is in the back of our textbook, table appendix J.1. All it is that resistors, as you know, having worked in the lab, E188 lab also, resistors come in standard values, right? And there are 1% tolerance resistors and 5% tolerance resistors. And the reason I brought this from the back is because as you do problems, you're generally asked to pick values from here. So for example, 10 to 20 and then 20 on, you don't see 21, 23, the odd numbers have disappeared. Similarly, if you go into the 40s, there's only 43, 47K, and so on. So only some values are available as available resistances, and in problems you are asked to use these, which means that whatever calculations you came up with may have to be slightly modified once you pick a resistance from this table to use in your circuit. Okay, so we'll worry about it when we start doing problems. Let's get back to our three basic configurations, and here they are. So there is the common emitter configuration, the common base, and the common collector. Now this is the one that we have worked with a lot already. In fact, a lot of the theory of chapter 6 that we studied in the previous course, 280, and I did some review also of this in weeks 1 and 2. So this is what we have looked at so far. These two may be slightly new to you. All right. So when we say common emitter, what that means is we are implying that the emitter is grounded. Okay. Similarly, common base, the base is grounded. Here the emitter is grounded and the input signal is put between base and emitter. Similarly, common base, the base is grounded and the input signal is between emitter and base. And the output comes out from collector and base, right? Collector and base. In common emitter, the output V0 comes out from collector and emitter. So whichever is the terminal that we have grounded, both the input and the output are with respect to that terminal. That's what you have to understand when we talk about common. Lastly, the common collector. The collector is grounded. The input signal is between the base and the collector, and the output signal is between the emitter and the collector, right? V0. So that's the understanding, and all these circuits are drawn with the biasing arrangements not shown. So make sure you understand that idea. These are only signal circuits. They're not biasing circuits, they're not total circuits. So we know that biasing exists using DC values, DC sources, battery and so on. But we kind of ignore that when we do a lot of this analysis that you see here. So the amplification analysis assumes a strong, stable, appropriate, proper bias point, Q point, and then the input signal and the output signal, always shown in small characters, only are discussed in these drawings. Okay? All right. So next section, 6.6.2, is characterizing any amplifier. This is kind of general. Any amplifier, whether it's BJT, op amp, or FET, MOSFET, there are three important properties of an amplifier. So even before we discuss the CE, the CB, CC in detail, in the textbook in 6.62, he has introduced you to the ideas of input resistance Rn of an amplifier, the open circuit voltage gain, AVO, of an amplifier, and the output resistance RO of an amplifier. So any amplifier has these three important properties that you should understand. So if you look at the generic drawing of an amplifier, you know this is an amplifier, right? It can be implemented using anything, any device, but it has an input side and an output side. The input side brings the signal. Generally the signal source has a inbuilt resistance. You cannot avoid this. Similarly, on the output side, you can talk about open circuit voltages and currents, but at the end of the day, you need a load. You apply a load, you attach a load, so that some benefit comes out of the amplifier. So the voltage across the load is the output voltage of the amplifier, VO. So what is input resistance Rin? Rin can be defined as the voltage at the input of the amplifier divided by the current going into the amplifier. So that's VI by VII. And VI can also be written, now this is the numerator. So VI, as you can see, is formed by a voltage divider consisting of this Rin going into the amplifier and R signal, right? So the V signal gets dropped to VI using the voltage divider formula. So make sure you understand what VI is and how it's different from V signal. Then we come to open circuit voltage. Actually, there's a few other gains, but this is the open circuit voltage gain, AV0. The simplest definition of AV0, it's V output by V input. Only, so the V output is here and V input is within the amplifier, right? This V in, VI, not the V signal but the VI. And if you replace this blue amplifier using one of the models, for example the pi model that we have studied, it also consists of three elements. The model, I mean, there's an input rectification resistance, there's an output resistance RO, this is Rin, and there is a dependent source. In this case, it's a voltage source which takes a factor AV0 and multiplies your input voltage by that, right, to generate a voltage here, which is then dropped across these two. So this AV0 factor is the open circuit voltage. Why? Because if there was nothing here, no RL, then VO would just be this, right? What you measure here would just be that, because there's no current flowing and RL is open. So the open circuit voltage gain AV0 is V0 by VI with RL equals infinity. Now there's another voltage gain that is defined, which is V0 by VI with some load resistance RL, not infinity but actual value, and that can be written in this form. So the actual voltage gain consists of the open circuit voltage gain multiplied by a factor RL by RL plus C. This will always be less than 1, right? So this factor gives you voltage gain, AV. Now we can write the output voltage V0 in terms of AV0 in this form. This is used in some problems, so I'm showing it to you here. Then we talk about G's, which are also voltage gains, but they are defined slightly differently. They are defined with respect to V signal, right? So the output voltage is pretty much the same as previous cases, but the input is now with reference to V signal, not just VI. Okay, so if you want to look at GV defined as V output by V signal, and the formula for GV is in terms of the voltage gain AV, it can be written as AV into Rin by Rin plus R sigma or signal. So various forms of gains. I know some of this we have already studied, some may be slightly new, but as we do some problems, the ideas become clearer. Then there is the output resistance, which we have already seen here, and this circuit is supposed to help you understand or determine RO. If you know the voltage and the current, then you divide, you will know the output resistance. Because it's an internal thing, it's not easy to measure, but sometimes it's possible to measure it like this. By putting a known source, looking at the voltage measured across it, and saying, that's RO. Okay. Alright, so these are your main important properties of any amplifiers, and now we'll start looking at each of the three models or the three configurations, the CE, the CB, and the CC, and maybe understanding again the three properties, the input resistance, the output, the voltage gain, and the output resistance for each of these three. Alright, so before we get started, I hope your memory of the small signal model is still fresh. If not, go back and study the previous sections of this chapter. Look at all the notes, my PPTs, etc. But make sure by this point you understand the small signal models well, because we'll use that quite a bit. So here's a summary of the formulas that in the small signal model. What is this transconductance? It's the IC by Vt, the bias current in the collector, divided by Vt, which is a constant, right? 25 millivolts. So the transconductance is strictly a function of the collector bias current. Similarly, the R pi, which is the input resistance here, is beta, which is a property of the transistor, divided by Gm. Finally, the RO, the output resistance, is VA, which is related to the early voltage, you may remember. So RO appears sometimes, but not all the times in problems. But if it is given, VA is given, then you divide that by IC, the collector current, and you get RO. So these three are in the blue are your small signal parameters. So when we talk about the amplifier, the CE amplifier, which again has the emitter is common, the input signal is applied to the base and the emitter. The output signal is picked out from the collector and the emitter, right? And you know that the collector always has a RC, the collector resistor, to set the bias current. So the voltage output appears across the collector, but also appears across the RC, and actually it appears across RL also, because that tends to be in parallel in most amplifier configurations. So I show the RL also. So if you replace this transistor here, NPN, with the small signal model, this is what the circuit becomes. And we know that the input voltage is nothing but, sometimes also shown as V pi. So Rn in this case is R pi. RO is parallel combination of big RO, which is the output resistance, is a parallel combination of RC and small RO, which is the internal output impedance. And then the factor Gm into V pi is actually a current, right? Because transconductance is current by voltage times voltage gives you current. That's why this is a current source. You can see that here. And this current value is actually nothing but the signal IC. Signal plus bias together. which is beta times IB, right? So, well, actually, hold on. I should. Yeah, this is from the properties of the transistor itself, right? We know that. So anyway, I brought these formulas together so that you understand how we go about analyzing this amplifier. Okay. So in this model, anytime you're shown an amplifier, it's understood that you will solve it by using the small signal parameters. Okay. And that the goal is to somehow find the input resistance Rn, the output resistance Ro, and some amplification factor such as open circuit voltage gain or closed or voltage gain, overall voltage gain, meaning all the way to the output voltage divided by the signal voltage. So some such gain has to be calculated. Okay. So here, for example, we are still on the common emitter amplifier. You can see that the voltage output is written in terms of the transconductance and the input voltage in this formula. And again, as always, I am not going through the derivation of a lot of these formulas. I will leave that up to you to read the derivations, read the chapter. It will give you a lot of benefit. It will help you understand the material much better. But again, to solve problems, we will use these formulas. Some of the formulas are easy to see what the logic is, why they seem to be like that, but sometimes you don't see it unless you go through the derivation of the formula in the textbook. So I'll leave you to do that, but I wanted to show you that again, when we are analyzing these amplifier circuits, the three characteristics, the input resistance, the output resistance, and the gain, are what we are focused on. Okay. Now at the end of this section, there is a summary table of all the formulas for, in fact, let me show you that right now. Yeah, here is the table. Table 6.5, characteristics of BJT amplifiers. So the Rin, the open circuit voltage gain, the RO for each of these models or the configurations, common emitter, common base, emitter follower or common collector, and an extra one which is a common emitter with a resistance in the emitter circuit. So for these, the formulas for these three important properties, Rin, AVO and RO, and then the formula for also AV, which is with the load connected, and GV, the overall gain, it's all nicely summarized. And again, the derivation of each of these, I'm not walking you through it. They are generally just KVL, KCL applied and some circuit analysis. It takes a lot of time to go through each one of them, which we don't have. But if you get some time, at least walk through one or two of these derivations, maybe just for the CE, so that you know what logic is being used. But you must become familiar with this table. Okay? All right. So that's all I'll say for now about that. Yeah. And go back to slide 9. So slide 8, we just talked about the basic CE amplifier, 8 and 9. Now we come to slide 10 and we talk about the CE amplifier with an emitter resistance. So a new component Re has been introduced. So if you look at the previous circuits, there is no Re, right? Emitter is directly grounded. But if you put a resistance in the emitter, a lot of good benefits come about. And here's a good summary, a collection of the important benefits. The input resistance is increased, which helps in most cases. One disadvantage is that the voltage gain, AV, is reduced actually. But the other benefits are that the distortion or the risk of running into the non-linear portion of the input-output voltage characteristic, that risk of becoming non-linear goes away, or at least reduces by using an emitter resistance. So you can stay linear even though your input signal is larger. So with an emitter resistance, you are able to handle a larger input signal without distortion, without changing the shape of your sinusoid or whatever is your input signal. So that's the big benefit of having an emitter resistance. It helps you to create a cleaner amplifier without distortion. In fact, at higher frequencies, this is even more important. The high frequency response of the amplifier is significantly improved. Last but not the least, very important benefit is that the gain is less dependent on the value of beta. Now you know that if you buy a certain type of transistor, the beta values that are given to us are never just one value, right? They won't say 50 or 100. They'll say the beta values of this family of transistors goes from 50 to 200 or something like that. So you have to design a circuit even though one of the most important factors is so widely varying. And how do you do that? One tool that we have is to introduce a resistor in the emitter. Okay? So that's the benefit of having a CE emitter, common emitter amplifier, with one extra component, which is the resistor in the emitter circuit. Let's then look at the common base amplifier. The CB amplifier has a certain unique properties. This is what the CB amplifier looks like, right? The base is grounded, common base. The input is between the emitter and the base. The output is between the collector and the base. It has a low input resistance and a high output resistance. One of the applications of the circuit, of the CB circuit, is to amplify a high frequency signal that appear on a low resistance coaxial cable. So coaxial cables only have which are used a lot for television, audio signals and all that in your home applications. They have a 50 ohms to 75 ohm resistance, which is pretty low. If you put a regular amplifier like a CE amplifier, there'll be a huge mismatch in impedances, and you know that by the rule for maximum power transfer, input impedance should equal load impedance, or output impedance should equal load impedance, right? That's called impedance matching. So many times the output impedance of the previous component, such as a coaxial cable or whatever, you can't control it. It's either high or it's low. If it's high, you can just use a regular CE amplifier, which is the best. But if it's low, you need a way to match it. And so the CB amplifier basically does the job of taking low voltage or low impedance inputs and matching it to another circuit, amplifier circuit, which has a high input impedance. Okay? That's the big reason why CB amplifiers exist. Alright, so Rn is shown here, Vi is shown with reference to the emitter, on the emitter with reference to the base, which is grounded. The output is still coming out of the collector, and the model we use here is the T model, not the pi model. And in the T model, we deal not with Gm but with alpha, right? And Re, which is different from R pi. So these two parameters appear, and generally you'll notice in the textbook, whenever there is a resistor in the emitter circuit, we switch to a T model. It makes the job easier. Okay? Alright. So using this, some formulas have been derived, which I'm not showing, but they are in the table that I just showed you. Let's move on to the next very important configuration, which is the common collector, and it's also called the emitter follower. So what is a common? Well, before we even go into it, let's talk about something called a unity gain buffer amplifier. So what is a unity gain buffer amplifier? The unity gain means the voltage amplification is only 1. So what's the benefit of having a 1 voltage amplification? Again, it has to do with matching impedances. In this case, let's say a signal source delivering a signal of good strength, 1 volt, has a large input impedance, right? It has 1 meg as its source impedance. Previously, when we studied CB, we said the input impedance, when it's low, the CB amplifier is useful. The opposite here. When the input impedance is very high, too high, and you want to match it to a modest load impedance, like here 1K, and you can see the math here is very simple, voltage division. Here, without any matching, the 1 volt on the input becomes 1 millivolt on the output, which is totally a waste of signal, right? Here, by using this buffer unity gain, you are able to use most of the input signal, which is 1 volt, 0.9 is coming out onto the load. That's why the buffer amplifier with unity gain exists and is useful and is used a lot in circuits. So the common collector configuration gives us that function of a unity gain buffer amplifier. It's also called the emitter follower. What that means is whatever is on the input, the base, in this case, we attach the input comes in onto the base. Whatever is on that input base comes out exactly on the output, which is the emitter. That's why the emitter follows the signal. Hence, it's called the emitter follower. Okay? Because the gain is 1, right, as I told you, so nothing is changing as far as the signal goes. No sign change. As you'll notice here, GVO, the overall output to input open circuit gain is 1. So the same thing that's on the input comes to the output. Okay? Alright. So a couple other important things to understand how this emitter follower functions. The reflection property is something to remember. So we have seen this somewhere like in a transformer, right? When we were doing transformer circuit analysis, the load resistance is reflected onto the load resistance or load impedance, which is on the secondary of a transformer, is reflected onto the primary, and we use that property to solve the primary circuit. Same concept here. The load resistance RL kind of gets attached to the input resistance Ri, Rin, through the property of reflection. So the Rn becomes beta plus 1 times Re plus Rl. If you didn't have this connection, if you just looked at a common emitter CE amplifier, Rn is basically Re, right? But here, because we connect it in this way, this reflection is possible. Reflection is in both directions. You can look at the load resistance from the input side. Similarly, you can look at the signal resistance, our signal, from the output side. There also reflection happens. So here, to reflect the output side to the input, you multiply by beta plus 1. To reflect the input onto the output side, you divide by beta plus 1. Okay? So both are possible. And sometimes this RL is replaced with, if there is a load and there is an RE circuit or RE component in the resistor in addition to the RL in the emitter, then, and we are asked to also consider RO, then RL in this formula is replaced by this combination. Okay? Alright. So there's a lot of analysis using Thevenin's models and all that. I'm not going to have time to look at all that. But this analysis tells you or helps you finally come out with the exact formulas for R out, for example, which is R in, Re plus R signal by beta plus 1. Similarly, this is the output resistance. Similarly, the input resistance. And luckily, the voltage formula, the voltage gain is 1. The unity gain amplifier. Okay. All right. So here is the summary of everything that we have studied so far. Common emitter with a resistor, common base, emitter follower. Spend some time, make sure you understand each of these. Also the difference between AVO, AV. AV is when a load resistor appears in the formula. Similarly, overall gain. Now even for an emitter follower, the overall open circuit gain is 1, unity. But once you connect a load, then it's not 1 anymore, it's this value. Okay? So all these formulas are derived in the textbook. Take some time, but for my purpose, to solve problems, we're going to use that table quite a bit. Okay, so characterizing amplifiers summary. The CE configuration is the best for realizing most of the gain required in an amplifier. Let's say you're building an audio amplifier. You like music, you like singing, you need an amplifier so you can broadcast to the whole university. So you'll use a lot of CE amplifiers because they give you the gain. But in addition to using CE configurations, you will have to use CB and CC. The CB helps to take low input resistance, like your microphone, and attach it to the CE amplifiers. Similarly, this should not be CE, this should be CC. Audi personal. So that's a CC. So with a CC or emitter follower, you can do impedance matching to your speaker. The speaker always has a low resistance, low impedance. And so you can take your CE amplifiers that now the signal is at a very high value, and that signal can be sent to the speaker, but you'll need the CC amplifier in the middle. Okay, so this is a good summary of all that we have studied so far. All right, we have many numericals, exercises, problems that we'll come back to. There's 5 more minutes to finish up some important stuff here. Biasing, right? I think we've already studied biasing. Biasing is to establish the proper cue point, right? So that the amplifier can work on either side. Remember all those drawings I showed you? The signal comes in on the input from here, but you don't want to go into the nonlinear portions of this characteristic. So the fact that the beta varies so much has to be taken into account. So you must find a proper cue point. So we studied some basic biasing methods previously, including this. I mean, one thing is to say just there is a base voltage VBE, right? A battery, and that gives you a bias voltage. That is the simplest. Then you have this voltage divider concept, which also we have studied. All these are not so great because they will not give you good circuit performance across many devices. So what are the better ones? Here are the better ones. This is called the classical discrete circuit bias arrangement. It uses the voltage divider with 2 resistors on the base circuit, but in addition you bring in an RE. So with this combination you get one of the best, or at least the popular biasing arrangement. So we'll spend a lot of time. You see the formulas, I think we are familiar with them, but there are some new formulas that have been derived, such as, for example, IE is VBB minus VBE, VBB divided by RE plus RB by beta plus 1. How do you get VBB, which is, the voltage going into the base? You just take the VCC and do a voltage division. Similarly, you have the I base, I collector, and I emitter. You have formulas for all of them. So this, we'll do some problems on this, and the R base is R1 in parallel with R2. So these we'll use a lot, this particular configuration. There's also a 2 power supply version where this is plus VCC and the emitter power supply is different. This is more expensive obviously because you need 2 different power supplies, but it works better. Similarly, there's a third method where a resistor is used in the feedback resistor between the collector and the base. That's one method. A very advanced method uses a fixed current source, a constant current source in the emitter circuit, and to get this constant current source you have to use what's called a current mirror with 2 other transistors. So these 2 transistors are strictly to give you a constant I that you then put in this circuit. So this is a more advanced biasing method, which for the moment we are not going to worry too much about. So we'll use this method the most. Okay. All right. After this section is actually taking all the ideas that we have studied so far in the entire chapter and actually building complete circuits, CE, CB, or CE with an emitter resistance, C common base, which obviously I made a mistake. B, and the collector CC or emitter follower. So all these circuits we'll see, including coupling capacitors, which we have talked about also. Coupling capacitors block DC, but they allow signals to go through at any frequency. So for all these examples, real circuits, we will do problems to understand what gain is possible, what input resistance and what output resistance are possible. Okay, so much of this section 6.8 is all problems, and we will come back in our next recording and do these problems. There is one last section called amplifier frequency response. There's not too much material here. We've already studied some frequency response in previous courses, but we will do a whole chapter, chapter 9 in this course on frequency response. So I'll just wait to cover all this frequency response stuff, when we come to chapter 9. Okay, so that's it for this. In my next recording, we'll look at problems related to BJT amplifiers.